Okay, so time to finish off chapter 8, and this video is going to be a two-parter, and hopefully it'll go by pretty quick. I'm not going to go into too much depth here. So basically, section 8.4 is just about, how a developer, or some of the things that a developer has to keep in mind within the context of, putting together a knowledge base, right? And gives you some more terminology like, what's knowledge engineering, for example, and what's the process that a knowledge engineer would go through to build a knowledge base. And the section gives a couple of examples. I'll just highlight the first one. The second example in the text, I'll leave to you to review on your own. So the first part is going to be section 8.4. And then the second part of the video, we're going to talk about expert systems. And the expert system is going to be the focus of your final major programming project. And both section 8.4 and the presentation in part 2 on expert systems are going to come together, and hopefully you'll have some light bulbs going off, or some, whatever in your mind. You're like, oh, okay, I'm starting to get this now, kind of a thing. Because, you'll use Prolog to serve as the inference engine, and you'll put together the knowledge base by writing Prolog statements, and then you'll have a user interface which will take the form of the interpreter. Okay, and so you'll just have to convert some of the knowledge that you're going to put together through your process of doing research for your expert system. Make sure you format in the right way in terms of Prolog syntax, and just go from there, right? So that last programming project, hopefully it'll be easy. Hopefully it'll be really freaking easy. Hopefully it'll be a gift. I'm trying to give you a gift here at the very end of the semester. Okay. Anyway, so on to 8.4, and then once we finish this, we'll move on and talk about expert systems. Okay. So knowledge engineering in first order logic. So what's knowledge engineering? Well, that term just refers to the process that you go through when you're building a knowledge base. Right, so there's a process, right? Kind of like a software development lifecycle, or your approach for designing an object-oriented system, kind of thing. So you have a person who is a knowledge engineer, okay, and when you're putting together an expert system, you can take the role as that knowledge engineer, and that's just somebody who does some tasks. What are they going to do? They're going to investigate some domain. They're going to learn some important stuff related to that domain. Then they're going to come up with a representation of objects and relations within that domain. Okay, and so we've learned about how to represent these things by talking about, all this logic in the past few videos. Okay, so want to take a look briefly at the process for creating a knowledge base that has a domain that's well defined, and where you know that you're going to be making a bunch of queries against that knowledge base, right? Asking that knowledge base questions. So how about that knowledge engineering process? If you've had some of my classes in the past, I talk about what the process is for developing software, right? I always boiled it down to 3 steps. Step 1, understand the problem. Step 2, come up with a plan. Step 3, implement the plan, right? By writing your software. Well, same kind of deal, right? So the process of performing knowledge engineering, there's some steps. So what are you going to do? Well, here they are at a high level. Identify the task. What is it? What is it that you're trying to do here? Right? Then you want to go out and put together all of the relevant knowledge for dealing with that task. Come up with a vocabulary for those predicates, functions, and constants. Right? All that stuff we were just looking at with first order logic. Encode that general knowledge about the domain, right? By coming up with symbols that are going to represent your knowledge. Encode a description of the specific problem instance. And then once you've done that, once you've got a vocabulary, right? Once you've figured out a knowledge representation language, once you've then come up with symbols to represent that knowledge in the domain, Okay, then you can put together some queries to see if the answers you get back make sense. And if they don't, well, it's time to do some debugging, right? So identify the task. Let's look at this in a little bit more detail. Figure out the range of questions that can be asked, right? So what are the types of questions that you can ask your knowledge base, right? Figure out all the types of facts, right, that are available. So a couple examples. Does the WUMPUS knowledge base, does it need to be able to choose actions? Does that knowledge base need to be able to answer questions about the environment? Does that knowledge base need to tell you the location of the agent? Right. So those are 3 examples. So this is kind of like the PEAS process that we looked at, 5 chapters ago, 4 or 6 chapters ago. You're trying to flesh out what it is that you're trying to do here. Then you need to go out and assemble the relevant knowledge. So you, as a knowledge engineer who's designing this knowledge base, you need to be an expert within the domain that you're working. Or, failing that, find some people who are, right? Maybe perform some interviews and gain the knowledge that you need. So you extract that knowledge through this process that the text refers to as knowledge acquisition. You're like, oh my gosh, this sounds so complicated. No, it's just requirements analysis. You're getting a rough idea. So you're trying to figure out, well, what's the scope of the knowledge base? What are the rules that this particular world can operate in, or that it operates under? For WUMPUS world, this was really easy. It was a good little toy example to go through and just communicate the concepts. Other domains, real world domains, a lot harder, as you can imagine, and get really, really complex. Decide a vocabulary of predicates, functions, and constants. So all the domain level concepts, right? Everything with the domain, you need to translate that into names, right? So this, just like so many other things with software development, computer science, it's an art. More of an art than a science. A lot of times it boils down to style and how you like to go about doing things, how you want to name things, what types of, how you want to state your rules. There's a whole lot of right ways to do this. Okay, there's always more than one way to do something in computer science. Almost always, right? You can write the same program, the same C++ program, maybe 27 different ways because of how expressive the language is. So some example questions that give you an idea of what we're talking about here. Should PIDs be represented as objects or unary predicates? Should the orientation of the agent, should that be a function or should it be a predicate? Should we make the WUMPUS's location depend upon time? Right? So once you've decided these things, then that provides the ontology of your domain. Right? So what's ontology? It's a particular theory of the nature of being or existence. Okay? So you're trying to flesh out what the things are in this world and what their nature is. All right, so encode general knowledge about the domain, get all your axioms together for all the vocabulary terms. You're trying to come up with meanings for those terms, and once you have some meanings in your head, a rough idea, you can go to your expert, if you're not the expert, and verify that it makes sense. Right? And at this point, as you're going through that process and say, I have these axioms, for all my vocabulary, for all the terms I'm going to be using, hey, expert, does this make sense? And through this process, of verification, you can get a better idea of any issues that cropped up. Maybe you're not representing things cleanly. Maybe there's too much ambiguity. Maybe you're going to have to go back and repeat that previous step to do a better job. Okay, fine. Just like anything else in software development, it's an iterative and evolutionary process. All right, so encode a description of the specific problem instance. You got a good ontology. You've done the previous steps well, then this will be easy. All you have to do, write some atomic sentences about the concepts that are already part of that ontology. The problem instances themselves, the logical agents can supply those by using their sensors, right? Trying to figure out what's going on in the world in this particular, what are my percepts for this particular instance in time? And so what is going to be my action that I should take here? All right, so so-called disembodied knowledge bases, sometimes you can give additional sentences to update that knowledge base, kind of like in C++ programs or Python programs or whatever. You ask the user for some input. Okay, so that's not the same as if you have sensors that are automatically sensing everything and providing new information to the agent as it goes, right? As it proceeds through the world, right? So then you want to pose some queries to your inference engine, to your inference procedure. Now, remember we went through and we examined algorithms previously for how or to accomplish inference when we talked about entailment, for example. Right? So you can pose some queries, ask some questions. Let that procedure work with your axioms and facts to derive those facts we want to know. Where is the agent? Is there a PID here? Now, there's no need to write an algorithm that's specific to a particular application. We already looked at algorithms. Inference is inference in logic. Okay, it's going to work. Apply these techniques, apply these concepts. You don't have to reinvent the wheel. Right? So once you've tested your knowledge base, asked it some questions, you might need to debug the knowledge base, right? Almost never, right? How many times have you written a program perfectly the first time and never had any logic errors with it? Almost never, right? So you have to go through and you have to test and you have to debug. Now, you may write your knowledge base correctly based off of the knowledge that you have, based off of how the expert interviews went, based off of how you acquired your knowledge. But maybe the user is trying to use your knowledge base in a way that you didn't expect. Okay, you might have to go back and refine, repeat some of those steps. Okay, and another problem that could crop up, if you have some axioms that you need, but you didn't think of them as you're going through the process, so you didn't include them. Some queries that a user might ask of your knowledge base, you might not be able to get an answer because there were certain axioms that you forgot to include. Okay. Now, axioms that are missing or weak, you can identify those when you have that chain of reasoning, right? The search algorithm, we looked at a couple of different ways that you can do proofs. One way is going through and using a traditional search algorithm, and another was by doing an actual proof, right? And so if you have missing facts in your knowledge base, right, then some proofs won't be provable, right? You won't be able to prove some things. And so as you go through those steps of converting the logical equivalency, or maybe the truth table enumeration algorithm as it's going through, if it quits when it's not supposed to, that can clue you in that you're missing some information in your knowledge base. Okay. Now, incorrect axioms themselves, those are easy to find because for some world that you're talking about, they evaluate to false, or they themselves are false statements about that world. So it's pretty easy to filter those out, right? So, for example, the Wumpus world, if there's a pit in an adjacent square if and only if the square you're in is smelly, right? And so if that evaluates to false when it's supposed to evaluate the true during your testing, well, then you have a situation where you have a sentence that's incorrect and you have to go back and rewrite that sentence. All right, so section 8.4.2 goes through and gives you a detailed example of this process. To save time, I won't do that, but I highly recommend that you just read through that section. So what I'll do here is I'll just highlight, some of the elements of this process with regards to, putting together an electronic circuit, right? You need to have a knowledge base that can reason about digital circuits. That's what this example is all about. So you got an adder, okay? So that's what figure 8.6 is. You know, if you haven't done designing circuits in a while, or maybe ever because you haven't taken a class on it, don't worry about it. What you have here is a diagram, though, of a circuit that's supposed to be able to do some addition. Right? So this is going to be a 1-bit full adder. So the first two inputs are the 2 bits to be added. The third input is a carry bit. First output is a sum, and the second output is a carry bit for the next adder. Okay. Don't really need to know all of that. Just saying it to provide context. Now, what's in this circuit? You've got 2 XOR gates, 2 AND gates, and 1 OR gate. Okay, so this is just providing for us some context for what we're going to talk about here in a second. So, identifying the task. Right? I won't go through every single one of these. Just get you started. Analyze the functionality. We want to know, does this thing add properly? Right? So, how could you test to see if it adds properly? Right? Well, if all of the inputs are high, what's A2's output? If all of the inputs are low, what's O1's output? You can go through and design tests for the current that you use as inputs to see if the outputs match. Okay, do you have any kind of feedback loops on your circuit? So how do you assemble the relevant knowledge? Well, what do you know about circuits? Right? Maybe you go out and you take a class on designing circuits, right? Or you hop on YouTube and watch some videos. Maybe you go to a website, tutorial website, whatever. Right? You're just gaining the relevant knowledge that you need to be able to put together this knowledge base. So what do we know about circuits? Wires and gates. Signals are going along wires into gate inputs. Each gate's going to output a signal onto a wire. There's 4 gate types for this particular adder. There was the AND, OR, XOR, NOR. There's 2 inputs and 1 output for AND, OR, and XOR, and then 1 in and 1 out for the NOR. Okay. Right, so from there, you just continue on with the steps. Come up with a vocabulary, that represents those things. Figure out what your predicates are, what your functions are, what your constants are, and then come up with some names in your logic to represent those things. Okay, and then just keep going, right? Just keep going. Record your axioms. We talked about this. Come up with your description for a specific problem instance. This stuff we talked about. Pose your queries and do your debugging. So, the presentation chapter is long enough. Again, go through section 8.4.2 and that's going to walk you through the above steps in as much detail as you need. Okay? All right, so let me go ahead and summarize for you what we talked about in this chapter. What's first order logic? It's a representation language that's got more power, right? It's more expressive than propositional logic. Now, we need languages that can represent knowledge to be declarative, compositional, expressive, context independent, and unambiguous. Right? Now, different logics, you're going to be able to tell them apart based off of their ontological commitments and their epistemological commitments. Remember we talked about that. I showed you a little table that laid out a bunch of logics, comparing them side by side earlier on in the chapter. All right, propositional logic commits to existence of facts. First order logic commits to existence of objects and relationships. Propositional logic is based around facts. First order logic gives you the ability to talk about objects and their relationships. Right, so first order logic builds on propositional logic. Okay, it's adding terms for objects and quantifiers. Remember, we looked at universal and existential quantifiers, and these things were able to allow for logic that's more powerful than propositional logic alone. A first order logic possible world or model has to have objects and an interpretation. Right? So we've got constant symbols that are representing objects. We got predicate symbols that are mapped to object relations, and we've got those function symbols that are mapping a function onto objects. Atomic sentences themselves, they're true if you've got predicates between objects that hold. Right? And if you have an extended interpretation, you've got a quantifier that you're doing some mapping with. You're mapping variables to objects in a model, and those interpretations are defining your truth. Okay, when you're developing a first-order logic knowledge base, what do you have to do? You have to go through a process. You got to analyze that domain, choose a vocabulary, and code axioms that can support inferences. All right, so that's the end of the first part. The second part, I want to go through expert system. Okay, and hopefully that doesn't sound too overwhelming to you, right? I mean, basically, what do you have to do, right, when you're putting together a knowledge base? You have to go out and become somewhat of an expert on what it is that you're trying to do, right? You have to, or you have to get together some people who are experts, so that way you can define some facts, right? Define some rules for that domain that you're working in that can help to describe the world, and then you use logic to encode that information, right, using the symbols and using the techniques that we talked about. All right, so let's do part two. All right, so let's do part two. And part two is going to be really quick too. We're just going to talk about the basics of expert systems, and I want to tie it together to Prologue. Okay, so we talked a little bit about the process previously that you go through when you're putting together a knowledge base. An expert system just basically has three pieces. Right? And those three pieces are going to be a user interface. There's going to be some kind of an inference engine that handles the inference for you. And there's going to be the knowledge base, right, that's made up of all the facts and the rules that describe your domain, right, that describe the possible worlds that you're working in. And that's what all the logic that we studied was all about, was being able to put those together. So rather than come up with my own presentation for this, I got lazy, so I just went out and stole one that I thought was pretty good. So here's credit to the original authors. This was in the public domain, so YouTube, if you're watching, please don't take down the video. All right, so overview, expert system. We want to talk a little bit. I'm going to go really fast. What's an expert system? History, components of the expert system, who's involved in the development of the expert system. And this last point is going to be a repeat of a lot of the steps that we just talked about a second ago, right? So what's an expert system? You got a computer program. It's got specific knowledge or subject-specific knowledge that was provided by one or more human experts, right? So you can ask it questions, and originally it was envisioned that it would take the place of human experts like doctors and whatnot. We talked about that at the beginning of the course when we went into the history of AI. Okay, so the history of expert systems, I won't repeat that because we did talk about this, a lot of this at the beginning of the semester. Early 70s is basically when this stuff came about, and you wanted to have, with AI, you want to develop computer programs that can think in some ways, and we talked all about them. Right? So in the 60s, again, we talked about that at the beginning of the semester, had these programs that were developed so you could solve all kinds of different problems. And remember, we talked about how they kind of hit a ceiling where they only could go so far with the breakthroughs that they had. Right? And in the 70s, this takes us a little bit further. People who are working with AI, they realized, hey, the ability for a program to solve problems, that's going to be tied to a certain extent, to a great extent, to the knowledge that that program possesses. So that program needs to have a lot of knowledge, it has to have good knowledge, and that knowledge has to be encoded in a useful way for the program to be able to solve problems in a useful way. Right? So if you want to make a program intelligent, high quality specific knowledge about some problem area is what you want to provide it, right? And that's what we've been talking about. Okay. All right. So in enters expert systems, right? So what are the building blocks? We're going to start seeing some terms again. Knowledge base, bunch of facts about the world, right? And what are sometimes referred to as production rules, right? So if then, okay, so what's the if then? Well, remember when we were looking at implications, okay, in the logics, right? So you have to have an inference engine, and That inference engine, we looked at algorithms for how you could run an inference engine. Right? That's what we've been doing in Chapter 8. Okay, and you need a user interface. Now, how is this going to translate into your program, into your programming project using Prolog? Right? So your source code is going to contain your facts and your rules. Okay, this right here is going to make up the knowledge base. Now, the inference engine itself is provided by the Prolog interpreter. You don't have to write that. Prolog provides that for you because the inference is universal based off of the rules of the logics that we've been studying. Right? And so, you won't have to write that part. You'll just write out all of the facts, all that stuff we just talked about, translate that into Prolog statements, right? And then the Prolog interpreter can do the rest for you. Okay, and a user interface. Now, you're not going to have to write a fancy front end for your expert system. You're not going to have to go out and write a Java front end or a C++ front end or a Python front end or whatever. Even though I provided a couple links, if you're interested in seeing how that works out, check the resources section on Blackboard, and you'll be able to read more about it if you want to. The user interface for your expert system, we'll just use the Prolog interpreter. That'll be sufficient, right? We'll use that interpreter to pose our queries, to ask our questions, okay, to get answers to whatever it is that you decide that your expert system should be able to answer. It's going to be up to you. So, an expert system where all of its knowledge is, that's in the knowledge base, okay? And everything kind of revolves around that knowledge base and its inference engine, right? And so expert systems, because the knowledge base is so central, sometimes they're referred to, or they're also known as knowledge-based systems. Okay, fine. All right, so knowledge is represented in a computer in the form of these rules, right? So there's an if part and then a then part, so implications. Okay, so the if part's got the set of conditions that you put together through some logical combination, right? So that's why we've been studying that logic, so you can form these things, right? So you can form those implications, so you can tie together some real world thing or some potential world and model it with logic, having symbols in the logic that are tied to something that you're trying to represent in terms of knowledge. Okay, so I want to represent a human being, so H, right, or King John. Okay, so if the if part is satisfied, the then part can be concluded. Right, and so when you're going through and you're looking at the Prolog code, the tutorials, right, these production rules, these rules here, you're going to see in the tutorials, they take the form of, you're going to see there's a colon and there's a dash, and that's how they exist, right? Facts are statements that end with a period, okay? And when we go through Chapter 9, we're going to start digging into that a little bit more, to get the content more intimately connected to Prolog a bit. But if you understand these ideas, what we've been talking about, once you go through a couple pages of any of the tutorials, hopefully it clicks. Okay, so flammable liquid, here's an example. Flammable liquid was spilled, call the fire department, right? So think of an implication, right? If material is acid, smells like vinegar, then that spilled material is probably acetic acid, or it is acetic acid, right? Think about those implication statements that we talked about. Right? So expert systems, depending on how they're written, they can be written to utilize forward chaining or backward chaining. We talked about forward chaining and backward chaining a little bit. Chapter 9 digs into both of those ideas in more detail, so we'll look at it. But remember, forward chaining is facts-driven, and backward chaining is goal-driven. We talked about that. The inference engine, that thing right there is trying to get answers from your knowledge base. And this is what Prolog is going to provide for you. You won't have to write one of these from scratch, right? You'll use the Prolog interpreter to do it for you. You'll provide the rules, you'll provide the facts in the form of statements in your Prolog code, and then you'll be able to run queries through the interpreter interface, and the Inference Engine will perform the reasoning for you based off of those facts and those rules that you provided in the source code. Right? So the Inference Engine, it's the brain that figures stuff out. Okay? There's a methodology for reasoning about the information in the knowledge base, and that Inference Engine finds your conclusions. It draws your conclusions for you. Right? Could be written a lot of different ways. We looked at different ways that computers can perform inferences. Right? We looked at multiple algorithms. You could write an inference engine in multiple ways. Again, you don't have to. So don't even try, just use the Prolog interpreter. That's why you're having the assignment in Prolog. So it should hopefully be pretty simple, because all you're gonna have to do is put together your knowledge, okay, and some queries, and let Prolog do the rest. All right, so user interface, you'd have to, normally you would, if this was gonna be an actual real system, you'd write a front end for it. So that way, your user can communicate with that expert system in a user-friendly way. You will not have to do that. Okay, and there's other features that expert systems might need to take into consideration, they might need to be able to provide. Being able to do reasoning with uncertainty. We talked about some logics that can do that. We also talked about fuzzy logic briefly. Your expert system won't have to deal with that. Okay, and your expert system isn't going to have to explain, how it came to its conclusion to you, right? So you don't have to worry about those features. All right, so who's involved with putting together an expert system? The knowledge engineer, which I just briefly talked about at the end of section 8.5. Computer scientist who is going through and designing and implement the programs that are using the artificial intelligence that are incorporating those techniques. Domain expert, right? This is the person who has the significant expertise. They know, right, about the domain that the expert system is being developed to work in, right? So we were just talking about this. We were just talking about the knowledge engineer, and you might have to be the expert, or you can go find somebody else who's an expert so you can gain that relevant knowledge. That expert might not even be a human being, right? So I put together a video that you have access to where I went through and built a very crude expert system based off of traveling around Costa Rica. Who was my expert? I went to a in-country domestic airlines website. They were my expert. Okay, and I looked up a bunch of flights and encoded that into my Prolog code. And Prolog was then able to tell me, well, can I take a bus from, my expert system, through the use of that Prolog Inference Engine, was able to tell me, oh yeah, you can take a bus from Quepos to San Jose and then hop on a plane from San Jose and arrive in Monteverde or whatever. Right? Who was my expert? It was a website. Okay, wherever you want to get that knowledge from, knock yourself out. Okay, so we talked about knowledge engineering. That process of doing the design and building of an expert system, that's knowledge engineering, right? So we talked about the knowledge base, but taking a step further to the context of expert systems, knowledge engineering, you're designing and building that thing. Right? So, knowledge engineering, human experts, or some expert, you have to identify some expert to leverage their knowledge so you can encode that knowledge within your expert system. Right? So another way of looking at that process, what are the characteristics of the problem, right? We went through all those steps as it was laid out in the textbook. Here's another way of thinking about it. So you got to figure out what the characteristics of that problem are. What's your intent, right? What are you trying to do? What's the domain? Okay, so the domain expert, knowledge engineer, you're doing interviews, you're figuring out what the problem is that we're trying to do. We're trying to identify the problem. We want to describe it. translate that knowledge, right, using logic. Now, we don't have to design an inference system, as I was saying, right? We don't have to design a reasoning structure. Prolog provides that for us. But the knowledge, you do have to translate that into a computer usable language. Again, that's where Prolog's coming in. All right. Now, we don't have to worry about uncertain knowledge reasoning process. If we were doing something more complicated, we would. Let's see here. Now, remember, once you've gotten through the process, you have to start doing some testing, right? The way the representation of the knowledge was done might not be conducive to getting you successful answers to your queries. Right? Take it a step further, if you didn't write the inference engine correctly, well, you might have some problems then too. So there's that debugging process you have to go through. Right? So how do you know when your expert system is finished? How do you know that it's good? Right? You can judge how well it works by comparing it against how well a human equivalent would answer the same kind of questions. Right? You query your expert system. Hey, can I take a bus from K-Post to Monteverde? Right? And it says yes, you can. And if that's true, right, then and it tells you that you can, then cool, it works. But would a human being tell you the same thing? Right? Is it operating on that same level of maybe the person who put together the bus schedules would? If so, then yeah, and then you can say it's probably working pretty good. All right, so just to summarize, some pros and cons, one versus the other. Humans versus AI, right? Human expertise versus artificial expertise. I mean, why? What's the point? Why even have an expert system? Well, if you think about humans, knowledge that you have dies with you, right? It's perishable unless you write a book or something. You got an expert system, well, it's permanent. As long as the hardware is maintained, it's not gonna go away, right? Transferring information from one human to another, it's tough. Think about all the years you had to go to school, right? And one thing that I learned, as I earned more and more degrees, was that the more I learned, the more I realized I don't really know anything, right? But with artificial expertise with an AI, it's easy to transfer information. Copy, right? Copy, paste. Documenting human expertise, think of all the volumes of books that have been written throughout the centuries. Okay, with AI, a little bit easier to do. Okay, through all the techniques of computer programming. Human expertise, unpredictable. If you forget something, or you made a mistake remembering something, or if you miscommunicated your expertise. I mean, how many times in lecture do I sit down and I say, or do I pause for a second, I should say, how am I doing? Did you guys get that? How are you feeling? Do I need to explain that again? With an AI, with an expert system, you're getting the knowledge communicated. You're getting questions answered over and over again consistently in the same form, over and over and over again. There's no human error there, right? Human expertise is expensive. Think about how much you have to pay to go to university, right? Once you can automate the process, once you can make cookie cutter experts, right? It's just a matter of reproducing the hardware and uploading the information into the hardware, and boom, you're done. So it's quite a bit less expensive to do this, artificially. Once you've got all the upfront costs of doing the knowledge engineering done, you can just clone machines. So some pros and cons, just some things to think about. All right, so there's some prominent expert systems. If you're interested, you can look them up on your own. Not required whatsoever. What I wanted to do with this presentation was just say, look, what's an expert system? Let me just summarize. Okay, an expert system, you're putting together some knowledge, okay, and you have to encode that knowledge in some way. And we looked at techniques for doing that. That's why we were studying propositional logic. That's why we were studying first order logic. Okay, and you have to get that knowledge together. You have to be able to express it in some way, and then you have to translate it into some computer language that a computer can understand. Prolog's the easiest way of doing it. Other common languages for this, believe it or not, Python, Lisp. And then you need to have some kind of inference engine. Either you have to program one yourself, or, as we're going to do, just use what Prolog provides. Okay, and then an expert system is going to need to have some kind of a UI for a user to be able to use it effectively. For us, we're keeping it simple. You can just use the interface from the Prolog interpreter. But normally you have to build something pretty sophisticated, using Java or C++ or some other tool to build a UI for it. You have to have a front end. How do you know when your expert system is working well? Well, if it can take the place of a human, then it's definitely working well. Or if it can perform, at a reasonably similar level for whatever it is that you're trying to do. You got a knowledge engineer who's responsible for putting this stuff together. You got knowledge experts or domain experts that you can consult to gain the relevant knowledge that you need. And I think that's about everything that I wanted to talk about, right? So their knowledge engineering was a process. You had to go through and identify what your task is. You have to assemble the relevant knowledge. You have to encode that knowledge. You then have to test to make sure that the knowledge. Do some queries against your knowledge base, make sure that the queries perform as you would expect them, do debugging as necessary. Okay, and that process is going to hold up for putting together an expert system, because an expert system has an inference engine that is making inferences, drawing conclusions based off of the knowledge that you provided. All right, that's chapter 8. And that is a mini presentation on an expert system which you are going to build.